Good day, folks. I'm Scott Parent. I'm the CTO of Baker Hughes's digital solutions business, and part of that role is also managing the responsibility of three of our research centers, globally located in Oklahoma, Houston, and Mumbai, India, where we do essentially a lot of new tech work around 4IR technologies, which I'll talk a little bit about in a few minutes. And look, I want to start by thanking Ansys for inviting me to this forum. It's an interesting time we're in, and frankly, from a logistics and a productivity standpoint, to have over 20,000 people registered for this conference says a lot about sort of the new way of working and what's possible in that new world. So that's also very exciting. And look, I'm briefly going to take you through Baker Hughes's digital transformation story. I'm not going to spend too much time on it, but I'm going to kind of lay it out in the context of how we're looking at digital transformation, both for our customers and our company. And then I want to talk a little bit about, in that respect, about how Ansys and Baker are working together, specifically in this space of transformation in our additive technology area, which is not only very exciting from a digital standpoint, but it's also very exciting from a standpoint of what it's going to do for our industry and our company in its transition. So with that, let me just talk a little bit about why digital transformation is so important to us. Our customers are facing into an unprecedented time of energy volatility. I mean, we've all witnessed what's going on in the oil and gas markets, but it's a bigger story than that. It's really about the energy transition from oil and gas focused and coal to more renewable, smaller carbon footprints, so carbon capture in our space. And all of our customers are challenged with how to get there sooner, faster, safer. How do they manage that in a position that is going to allow them to get there safely and quickly in terms of taking advantage of what it could be to be more productive in that space. So, our own company, Baker Hughes, has over 65,000 employees. We operate in over 120 countries. With 30 ERP systems and 27 product lines, our own business is quite complicated and digitally, quite frankly, disconnected as everybody else is as we work our way from what was sort of a hangover of the third industrial revolution, where we all created and used bespoke digital tools and processes that were not as connected as we need them to be today. And, one of the things we think about in terms of that new digital ecosystem is that it needs to allow us to collaborate instead of being a hurdle to collaboration. And we're working through that in the additive space with our friends at Ansys, and I'll talk about that in one of the examples. So as an energy technology company, Baker Hughes has been around for over 100 years. And we've become, frankly, a company that is looked to from our customers in the market as a company that continues to lead not only in the energy transition, but in the driving of new technologies at the edge. And when you think of the edge, and when we think of the edge, we think of all of that technology from drilling wells to gas turbines in LNG facilities to the measurement devices and digital solutions around our System 1 monitoring systems for condition monitoring. All of these technologies are out there close to our customers and at the edge of our customers. And many of them are monitoring historically old processes. Some new tech has certainly been delivered in the course of those 100 years, but there's an opportunity now to bring what I consider a bigger and better, tighter digital ecosystem that allow us to do more than just sell products, but integrated service solutions and helping our customers become more productive and efficient. And so when I think of Baker Hughes going forward in the next 50 years, how do we support our customers through that energy transition? The lower carbon footprint and higher level of productivity, it's going to be through new technologies and the capabilities those technologies bring to our products and our services. We look pretty simply at something we call essentially the improvement in process control through new technologies like 4IR. And we consider this at the heart of our digital transformation, both from our internal use of process and our external use of process. And for those folks who may not have a background in controls, this is the simplest version of a control diagram that we can consider. where we have some process at the center, and it's where in our case it's some highly valued industrial process, not boiling an egg, although that's a process. It's more around how do we start up a gas turbine, how do we inspect a pipeline, how do we improve what we're doing in terms of the time it takes to drill or complete a well. So these are the kinds of industrial processes that we look at from our business and our customer standpoint and say, how do we reduce waste? How do we improve the productivity of the workforce that's performing this process, or eliminate where possible from a safety or other opportunity headcount through an optimization. How do we improve emissions? I mean, these are all the kinds of outputs that we're trying to improve for our customers. And the 4IR technology is kind of shown here at the bottom of the page, not exclusive, but certainly the technologies that we are relying on in our industry are essentially the ecosystem of new digital tech that's allowing us to either improve the measurement or the analysis through AI or machine learning or control. And when we look at the way that we do any one of these process steps, and if you're a Six Sigma graduate, you'll see measure, improve, define, measure, analyze, improve, and control right here in the diagram. So, but if you want to improve that process, then we look at these technologies as a way to do that. And I take, for a very simple technology that many of you may be comfortable with, is CT scans. CT scans have been used for over a decade or more for both medical systems and hardware inspection. But today we're able to take image recognition and anomaly detection along with AI and do so much more with those images as a measurement, not just a collected set of data. It brings us a completely new set of measurement devices and the measurement capabilities, from fraud identification for banks on identity to plume analysis in an oil field based upon an IR image. So from when I look at these technologies, I look at them as collectively working together, although they're all on their own timelines and have their own, if you would, technology roadmaps and development plans. They're all very much integrated. And I think the same thing is true when I look at additive technology. You know, when I think of additive technology, what we're doing, and I'll show you in the next page or so with Ansys around large physics simulation, is giving us a view that we never had before. It's revolutionizing the way our engineers look at design problems and pushing a more digitally integrated solution. Form, fit, and function have become much more optimized against not just weight, strength, and cost, but also speed to market. You know, additionally, additive manufacturing, which is very much part of our customers' digital roadmap, is taking parts from manufacturing of months down to hours and days. And so when we think about what we do in the design cycles, we're also going to be challenged to take our design cycles down from months and years to days and weeks. And that's going to change and challenge our engineers to make sure that through that process, we don't get a less optimized product, but a more optimized product. And that's really where generative design is coming in. And I'll talk about that. You know, so many of you may be familiar or have heard of generative design, and I'm not going to certainly give you a lecture on generative design this morning, but I do want to talk about how we see generative design is taking additive from the future of manufacturing to the future of manufacturing and design. I think to additive, generative design is the enabler. And when I think of all of the enablers that feed into generative design, all of them are at our fingerprints today. Inexpensive, high performance computing is allowing us to do a lot more in the multiphysics arena than we've ever been able to do before. And this idea of AI-assisted design methodology has really opened up to what I think is going to be the future of design. It's going to be very exciting. You know, the approach is already being leveraged in several other industries like aerospace and automotive, where either weight or high volumes are dictating new design practices and manufacturing solutions. This new digital design ecosystem, you know, is enabled by some of the 4IR technologies. And if we pair multi-physics solutions, as I said, with high performance computing, we're allowed then to bring in machine learning and then that unique process of additive manufacturing to enable the ecosystem to significantly improve productivity. You know, and the old adage of mine was always, it's much better to model and make versus build and break. And I think at the end of the day, what we're seeing is this marriage of what we used to do in design for product understanding and modeling of that product in its application, to now being able to not only model what it will do in application, but to model through its inception. Below is a very simple, real example of something we did on one of the assemblies for one of our subsea assemblies. And just to share with you for our customers, and this goes back to the energy transition, every pound saved in material weight of these very large assemblies saves the size of boat and energy necessary to get things like subsea trees on the ocean floor, and that's a big deal for our customers. So when you think about additive design, historically, everything we've done on the left here has been in a world of subtractive, and so when you take that valve body, you'd say, boy, that looks kind of blocky, but if I were to remove any more material from it in a subtractive world, I would be paying for that. And if I put an engineer in front of that design and say, hey, listen, try to take some of the weight and size off that, and I have that engineer then go load in, let's say, some stress analysis and thermal analysis software and structural, and he can make some decisions about what and where we could take some material out of the part in operation. If I let an AI assisted, a machine learning, if you would, tied to the print capability of the machines we're going to manufacture these on, all the way out to the application, I can get an even significantly higher level of productivity in the manufacture of that part. 60% mass reduction, 40% of the cost. And what's been a problem for additive today is somebody will come to our organization, our team in additive in Houston, and say, hey, just print me this part on the left. And when you do that, you put additive at a significant disadvantage. And so unless you bring in generative design, you really leave additive on the table as being potentially a more costly solution, because you're not, in fact, taking advantage of the fact that you're generating by layer this part on the right. So pretty exciting stuff. We've seen in some cases up to 120 parts in assembly, I think has been our record so far, that we've gotten down to a singular part. And that opportunity has come because we've been able to work with using some of not only the analysis tools that Ansys provides for the end product, but also for the actual build. And I'm going to give you an example of that here. Ultimately, about 70% of the cost of producing a part in additive manufacturing is really time on the machine. And when you see today a part on additive, you'll see that in some cases you're replacing 3, 4, 10 processes that you would do on different pieces of equipment and setups in a standard manufacturing subtractive process. Over the course of the life of the machines that we've bought from OEMs, and this is not a particular machine, but multiple machines, where we're doing laser deposition, we've been able to improve through trial and error and design of experiments about 50% of the cycle time of what we used to run when we bought the machines just a year or so earlier. Using some of the technology now from Ansys around what we call the Ansys print and the Ansys science tools, we're actually able to explore the design space and the manufacturing space at the same time. And when we do that, we can optimize the parameters on the print machines to basically give us and dictate to us that we're going to get the right microstructure. We're going to get what we expect in terms of thermal compensation around distortion potentially in the part. We're going to understand stress strain and where we might have laid an inclusion or a void based upon particle count, size, and spacing of the lattice. To me, that's all very exciting. What's more exciting, however, is just through the last 5 to 6 months of using this technology, we believe by the end of this year, we'll have not improved by 50% the output of these machines, but by over 200%. And that is becoming to us to become very exciting, because it's making additive then more applicable where cost sensitive parts, not just shape or weight sensitive, can be addressed using additive technology. And I'll just quote one of the folks on my team when they told me a few weeks back. We were looking at appropriations, I should say, in December of funds and capital for 2020. And we greatly increased our digital spend in the additive space. And one of the first comments I asked about some of the new tools we brought from Ansys in terms of what's the return on investment here, folks, with these tools is weeks. We're looking at weeks of reduction or payback, I would say, on these tools based upon just the first applications, where not only do we improve the output of the quality of the part, but we improve the speed in which we made the part. Those things do not have to be in opposition, and Ansys has helped us get there, and is going to continue to help us get there as we qualify new materials and new applications on these printers. I would just say, look, kind of bringing it back to the digital transformation story where I started. What's so exciting about bringing all these technologies together is how we can actually transform our businesses. In the backdrop of this page, you see a drill bit. And historically, this drill bit would cut through the geology, in many places around the world, in oil fields and subsea, and gas fields as well. And the cutter structure that you see around that surface, these little black, look like M&Ms, or polycrystalline diamonds. And those are the cutting structure, and where they're placed in the orientation is really dictated behind the geology that we expect we're going to see when we go into drilling a campaign. What's kind of interesting, and I'm by education an aerospace engineer. Anywhere in the world 3 miles up, we have pretty much the same conditions. Now, we can have storms or anomalies, if you would, but by the most part, density, temperature, and these sorts of things, pressure, are not radically different. In fact, they're very, 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 very stable. When I go 3 miles down, we have a very different situation everywhere on the planet. And ultimately, when we design a drill bit, we do the best we can to meet the formation we expect to see. Now, if you look to the right, there's sort of this very circular design manufacturing pattern. Historically, this is a very linear process. We design something, we manufacture it. We don't necessarily know all the stress and strain that's applied in that process, although I will say that the models for modeling, forging, and casting have gotten a lot better, obviously, over the last few decades. But in that process, then we bring a part to the field. And then once the part's to the field, we operate that part through life cycle, gain some information about it, and usually bring that information back to the front end of the line and decide, what do we do differently? How do we design better the next time? How do we get a better part? What's really interesting about how this can transform our business is just in this example, we can potentially use generative design, or we have been using generative design, to create a much better bit. We can print using the density variation in the material and the printer capabilities, softer in some locations and harder in the other. In this case, harder on the surface, softer in the middle, like an M&M. But not only can we do that, and that improves and reduces the number of processes we need around cladding and some of the other things, but it allows us then to print the part in a location where the part's going to be used. Less central manufacturing, less logistics, again, less carbon footprint for transportation and those logistics, no customs, and frankly, giving local content to where the work is being done gives us much faster return on cycle time to our customer. Now we operate the part. We collect a lot of data on how that bit is performing as a rate of penetration, as a factor of how much pressure and vibration we're seeing on the bit. And we can take that information and use that in a way we've never used before. We scan the bit using 3D, basically an iPhone, and anomaly detect on image recognition to tell us whether or not we've seen too much or just enough wear on that bit to either replace it, recycle it, or repair it. And those options have historically been very objective, but now using 3D scan and image recognition, we can do that with a lot more confidence and precision. And lastly, we can bring AI to the picture. We can bring generative design back to the picture. And how this becomes more of a circle and not a line is today when we start that cycle, after we've printed the bit in location at 10 times the precision of a casted bit that's been machined somewhere in a central location in North America, we can then operate and compare operating and wear data and understand from an algorithm standpoint through design practices that go back 100 years what that new surface of the bit should be. Now, if we decide we're going to print a new bit, we can do a fit for formation bit. And we can do that in days versus weeks in the historical process. If we decide the bit's pretty close and we want to repair the bit, we can pull a Tom Cruise in Mission Impossible and reprint the face on that bit and have a fit for formation or closer to fit to formation bit than we had before. In fact, jumping in the middle of what would have been a historical operation and continuing back to a better level of performance. So when I look at a business transformation, this affects us the way we operate. This obviously affects the way we manufacture and where we manufacture. But more importantly, it affects what we do in the output of our customer. We will take what was maybe not the best run rate and improve that instead of in weeks and in hours. And that campaign then can be much more efficient and more productive. And this is just an example of how digital transformation, the tools of digital transformation, and the work that we're doing with partners like Ansys are allowing us to become and be ready for the transformation for the next 100 years. Thanks for your time. Again, I appreciate Ansys for the offer to come talk to you. It's an exciting time to be in engineering, and certainly an exciting time to be partnering in this world of digital transformation.